The following is an excerpt from the book Experiences of Thought by Anthony Kahn, available now on Amazon.com and Kindle. Lucrative Logic in Matters of Matter. Relativity. First things first, don't panic. Yes, as the name suggests, we shall be talking about time and space in this section, but we shall not be delving into Albert Einstein's famous theories in any mathematical depth. It is important, however, to understand that Einstein turned our classical, common-sense notions of time and space on their head. Where both time and space had long been thought of as fundamentally unchanging and largely distinct components of the fabric of our universe, Einstein united them into a four-dimensional, geometrical construct called space-time that has a dependency on velocity, acceleration, and gravity. His theories require the acceptance of concepts such as time dilation, length contraction, and the warping of space-time in the presence of matter, aka gravity. So we begin this section by noting that neither time nor space really behave according to the rules that we intuitively imagine them to, based on our everyday experience. But for now, let us take a step back and consider what time and space really are. How fast are you going right now? It's a simple question, right? You are either moving and covering some distance per interval of time, or else you are stationary. But what is your frame of reference for gauging your velocity? It's probably the Earth's surface, for that is the largest single entity in our mind's rationale as we go about our day-to-day activities, and indeed the thing we find ourselves anchored to via gravity. But in modern times, we have the luxury of knowing that the Earth does not truly lie at the center of anything. And with reference to the wider universe around it, neither is it stationary. If you were to stand at the equator, your speed relative to the center of the Earth is higher than the ground speed of a cruising passenger jet. This is because of the Earth's rotation. Meanwhile, the speed of the Earth relative to the Sun is much higher still. All the while, the Sun travels with significant speed relative to the center of the Milky Way. And the Milky Way, in turn, travels with significant speed relative to the center of mass of the local group. The local group has speed relative to the center of mass of the Virgo cluster, the local supercluster, and on the largest scales, beyond the realm of strongly bound systems, everything is growing more distant relative to everything else as the universe expands. But the expansion of the universe does not imply some central point. Rather, it is commonly exemplified with reference to a loaf of raisin bread cooking in the oven. As the raisin and dough mixture heats, it expands such that every raisin in the mixture grows more distant from every other raisin. So what are we to make of all this complicated hierarchy of motion? You might have noticed that one word keeps popping up again and again: relative. No statement of motion or speed makes sense unless we specify what that motion is relative to. As Einstein so often did, let us embark on a simple thought experiment. Let us imagine an infinite three-dimensional space that is home to just one single particle traveling with uniform speed. Hang on a minute, does that actually make any sense? If we have just one particle moving in infinite space, there is nothing to measure its speed relative to. So how can it have any speed? Whether it is moving or stationary is actually not defined. So what is space then in this simple little universe that we have conjured for the sake of argument? Is it a necessary container for our particle to exist within? Or is it actually just a vestige of the way we have come to make sense of our vastly more complicated universe? If the particles that exist within, that which we call space, are actually the very thing that give it its dimensionality, then perhaps space is actually at a deep level, really embedded within the information that defines the particles themselves. Space can be a tricky thing to describe in a qualitative way, especially without relative reference points to define it, and time is no different. Just as we always occupy the point in space called here and define it with respect to other positions in space, we always occupy the point in time called the present and define it with respect to other times. Our location in time seems more involuntary though, for although we can travel back and forth through space as we choose, we must traverse time at a very fixed rate and in a fixed direction. Now, as already mentioned, Einstein showed that this common-sense perception of space and time is not strictly accurate. For one thing, you cannot separate space and time so neatly. In his special theory of relativity, he set out to provide a description of the universe's geometry, aka space-time, by requiring that we work with a four-dimensional lattice of events, rather than the more intuitive three-dimensional space evolving in time. Each event is simply a position in the lattice, with three coordinates representing space and one representing time. This situation is usually made easier to digest by thinking in terms of two-dimensional space-time diagrams. Essentially, these diagrams just look like your standard Cartesian planes that you would have encountered in high school, with the three spatial coordinates collapsed into one dimension forming the x-axis and time forming the y-axis. The plots are subjective in that they center around an origin that represents the here and now of a particular observer. We can divide this plot into two principal regions that we label time-like and space-like. Any position within the plane that could be reached from the origin without reaching or exceeding the speed of light is called time-like. This also applies to past positions from which the origin could potentially be reached without reaching or exceeding the speed of light. All coordinates that are not time-like are said to be space-like, with the exception of positions that are only reached by traveling at precisely the speed of light itself, which are called light-like. Any event that lies within the time-like portion of the plane can potentially share a direct cause and effect relationship with the origin. Meanwhile, any event occupying a position in the space-like portion is unknowable from the position of the origin. Now, this curious model may seem complicated at first, but mathematically it satisfies the requirements of observation, where the intuitive three-dimensional space does not. It does, however, lead to some rather outlandish, though proven, predictions. Chief among these is that measurements that we make of distances within space, or of the length of elapsed time, are actually dependent on our motion relative to that of the reference frame of the measured interval. What's more, even events that we observe accurately to be simultaneous, others, in a different reference frame, may observe to occur at different times. There's a caveat here, though, as causality will always be preserved, even within Einstein's relativity. This means that any event that causes another event will be observed to occur before that event, regardless of the reference frame. This persistent requirement ultimately leaves us with a fixed arrow of time, wherein time inevitably has a fixed direction. If nothing else, however, we can begin to see that time is not quite the simple and impartial continuous flow that we discern with our stopwatches here on Earth. Even the seemingly sensible concept of a universal present requires qualification. Moving on from considerations of space and time as a quantitative geometrical construct, what can we say about their scale? We have already seen that both space and time gain dimensionality as a consequence of the relativity of events. But how do we define a big space as opposed to a small space? And likewise, what makes a time span long or short? Again, it arguably comes solely down to contents. What does infinite space mean if it is devoid of any structure? What is an infinite span of time if it encompasses not a single event? Suppose you are comparing two simulated video game worlds, one taking place on a 100 square kilometer desert plain, the other simulating a much more modest 100 square meter backyard. Now clearly, the latter world is much smaller than the former, coming in at a paltry 1/millionth of the size. But suppose the latter world is experienced from the perspective of a microscopic probe with top speeds of millimeters per second, and renders every cell of every blade of grass in exquisite detail. Meanwhile, the desert plain world is a vast, empty environment with little to see or do and experienced only from the cockpit of a helicopter at altitude. Which world will you experience as the larger? Which world do you think would take up more space on your computer's hard drive? It is a similar story with time. Who has the longer lifespan? The person who lives 100 years, mostly in a comatose state, or the person who lives through just 50 years, though years brimming with activity and novel experiences? Arguably, the perception of how much time passes will be heavily dependent on the number of events experienced. Continuing with our pondering of time, however, there is apparently one major difference between how we experience space and how we experience time. Why can we revisit the same coordinates in space, but not in time? Why are we stuck with that arrow of time? From the perspective of Einstein's geometrical space-time model, this discrepancy goes away in a sense, as we no longer separate space and time coordinates. We thus end up with an inability to return to any full set of 4 space-time coordinates. But where are these inaccessible coordinates, specifically those lying in the past and in the future? Clearly, their existence is logically mandated by their causal link with the present, but do they truly exist if it is always the present? In the end, it seems to be, once again, relative. It is a question of perspective. To put it in simple terms, the present you is no more real and no more valid than the past you. The past you was once the present you, at which time the now present you was the future you. Essentially, you can only ever perceive events from that one golden position in space-time, those ever-persistent coordinates of here and now, the origin of the space-time diagram that we discussed earlier. But that position is no more significant than any other position in an absolute sense. After all, no two people ever occupy the same 4 coordinates of space-time, and you cannot say that their existence is less valid than yours unless you resort to metaphysical solipsism. So ultimately, asking why it is always the present that we experience, even though it is no more special than the past or the future, is tantamount to asking why am I here and not there? Though you may have been there, you are not there now, or you wouldn't be here. But there still exists. We just experience it differently when viewed from a different perspective. To reappropriate the words of Martin Luther, it is very much a case of here I stand, I can do no other. In the space-time sense, our mind's perspective is only ever one event, the origin of our space-time diagram, but our life is a string of contiguous time-like events. Our life is thus permanently etched into the fabric of space-time, but we cannot experience it instantaneously, all collapsed into a single present any more than we can be everywhere at once. It is enough to say simply that we experience it. Time and space are perhaps best understood as just a part of that experience, constructs of our own unique perspective. Throughout this brief discussion of space and time, we have considered these two intrinsically linked and ever-prevalent aspects of our reality, both in terms of science and pure philosophy. But regardless of our approach, one thing is clear. Both space and time, and indeed mathematical space-time, arise out of the relationship between events. Without content, without information, they are arguably meaningless. It would seem that in the end, not only are they inextricably connected with each other, but they are also inseparable from the information that they relate.